The first one was in terms of generating a uniform electric field, and so that we can calculate the field in terms of its elementary parameters such as the charge and the distance and etc. More recently, we started turning our focus onto the application of capacitors into electronic circuits, and that's where we discussed this idea of capacitance. And so we looked at the series orientation as well as a parallel orientation. But we're going to be continuing on to that in terms of its ability to store energy. So electric energy, energy storage. So it turns out that even though capacitors can store charge, that's primarily what it's used for. In a recent topic on electric potential, we saw how the potential was related to the electric field, but potential was also derived from the energy. So capacitors, with its ability to store charge, can also charge electrical energy. So charged capacitors can store electrical energy. And so that energy value has three different equations. However, one is more fundamental than the others. The amount of energy that's stored in a capacitor is equal to 1/2 times the charge squared over the capacitance. 1/2 Q squared over the capacitance. But an alternate way you might see this equation is simply when we utilize Q is equal to CV. Q is equal to CV. When we substitute Q squared for this, what do we get? We're going to get U is equal to 1/2. Q we replace with CV. It's C times V quantity squared over C. And as long as you guys remember the rules of exponents, and in case you forgot, you could just write it out the long way, meaning CV times CV. That's the definition of a squared. You just multiply it by itself over the capacitance. One of the capacitances cancel. And so you could also compute the energy stored in a capacitor by this expression 1/2 CV squared. And we go from this equation to this other one simply through our capacitor equation. Instead of replacing Q with CV, we can replace C with Q over V, which is still part of that capacitor equation. And if we do that, we get the third way we can compute the stored energy in a capacitor. So this would be Q squared over Q divided by V, where one of the Q's cancel. And so this is going to be 1/2 Q times V. And that will be the third way. Now, which one you use ultimately depends on the information that you're given in the problem itself. Now this is section 2C. We're going to move on to electric current. And what is called resistance. Electric current and resistance. Let's just remind ourselves of some basic terminology. The first one is electric current. This is defined as the flow of charge. The flow of charge. But how do you produce, or how do you make charges flow? So how to make, or how do you get charges to flow? So how do you get charges to move in general? And we talked about the mechanism. Even though they're long-range interaction, the interaction happens through an electric field. But we discussed electric field is a vector. We can use a scalar form that is directly related to the electric field by a voltage. So you can get electrons to flow simply by applying a voltage on, applying a voltage onto the charge. And this is why batteries exist, to get that voltage. So batteries exist to apply a voltage. Oh, we'll say potential difference. Which you call V. So that is the entire purpose of a battery. Here, a circuit can be made if conducting path is connected to the positive and negative terminal on battery. So a circuit can be made as long as you have electrical contact from the positive to the negative terminal onto the battery. And as soon as this is made, this will, because the battery applies a potential difference V, you're going to get electric current. So once circuit is formed, what you get is electric current. And electric current is given the algebraic notation capital I. Capital I. Where I is equal to delta Q over delta T. Or sometimes it's simply just called Q over T, which is defined as the charge, amount of charge passed through per, or divided by the time interval. So we can define how much electric current is having by just simply measuring. Let's say here's a wire and we're looking at this position right here, how much charge is passing through this point right here in a given time point, or in a given time duration, sorry. Just from looking at the definition, you should be able to tell me what the units of current is. Q has units of coulombs. What is a unit for time?
Seconds.
Right, seconds. It's coulombs per second, which is given by a different name called, or it's A, and it is amps. Amps. Named after a guy named Ampere, who was also very important in our understanding, in developing our understanding of electricity. Here, if path is broken, then I is equal to 0. So a continuous path is an absolute requirement for charge to flow. As soon as the path is broken, your current is going to be equal to 0, and this is often this is a pretty common issue when your electronic components, something breaks. Likely when you dropped your phone or whatever was broken, some path, because when it breaks, a electrical path has been disconnected, and so this entire device can no longer function, because even if one path is broken, well, depending on which one it is, you will not get charge flowing through, and it won't actually power your entire appliance. And this is defined as an open circuit, or a broken circuit. It's known by many different names. So essentially, it's just one where there is no flow of charge. Now with this, let's do a quick example, conceptual one. And it's regarding establishing a circuit. Establishing a circuit. Oh, I forgot to mention. No, it's okay. The question is, what is wrong with each setup? The first scenario A, we have our battery. We have our positive and the negative terminal. Positive is right here. And here we're going to be using a light bulb that looks like this. This is the light bulb, and this is conducting material. Conducting material. So essentially, we want to know, will the setup turn on the light bulb? We put a wire like this, and then we connect this end of the wire to the light bulb. In the second scenario, we have a battery, positive and negative. And here we put our light bulb. And in the third scenario, we have our battery, and we have our light bulb. And that is our wire. Let's look at the first scenario. Will the light bulb turn on? No. No. What is wrong with it?
It's not a circuit.
Yeah, it's Well, okay, and what, it's not a circuit in one sense. I saw some hands, it's not a, yeah, it's not closed. It is not closed, so it's not even a loop, right? It's not even a closed path. But there's a second issue.
It's not connected to the negative side.
Yeah, we need the negative. Where I say, yeah, okay, it must be connected to the positive and the negative terminal. So there's two issues here, not connected to the negative. What about for B? Well, in B, we have a slight improvement in that we now have a closed loop. But what's the issue? It's not connected to the negative. So not connected to the negative. What about this scenario here? Will this turn on? And yeah, it will turn on. So the answer is nothing. And here, all of you guys will charge me with asking a trick question, even though this is perfectly valid, because just because the question asked implies that something has to be wrong, but nothing can be wrong, which is a totally valid solution. But the reason why it's okay is this is a conducting material. And although you need a little bit of understanding of how a light bulb works, the positive terminal will go through here. So that we'll just follow the positive charge. Begins here, goes through the filament, and then goes to the wire, and then comes back to the negative. That's how it'll work. So in scenario C, nothing is wrong. It is closed, and it is touching both the positive and the negative terminals. So technically, this bullet point is kind of incorrect. And we already kind of, showed you guys why that's incorrect in one of the labs. And it's because in many circuits, you are connected to the ground instead of negative. So you're not always going to be connected to a battery. You might just be connected to some positive voltage source. And you still have a circuit. As long as you're connected to the ground, you still have a continuous flow of path. The ground has a circuit symbol in the circuit diagram. You might see it in one of two ways. One looks like this, or it is with a upside down triangle. And so if you have a circuit that looks like this, this is still considered a closed path. You still have a circuit because positive and negative, you have the conditions are met. A few other bullet points regarding current. One is that in a circuit, what is actually moving? What is actually flowing? What moves?
Electrons.
Right, electrons move. What charge does electrons have? Positive or negative?
Negative.
Right, it is the negative charge that's actually moving. But, historically speaking, this is before people understood electrons were a thing. People tracked the flow of positive charge. So people thought positive charge flow. So they were absolutely wrong in this understanding. It is the negative charge moving. Well, if negative goes that way, which way is positive going? The positive is just moving this way, but technically it's the electrons that are moving. And this is what came to be known as the current. So the current is not actually following the direction of electrons, it's following the direction of opposite electrons. It's tracking the flow of positive charge. So I is the flow of positive charge. Simply opposite the direction of electrons. Now there has been in modern days an attempt to define the flow of positive charge as like the traditional current, and then people tried to define the modern current, which is actually the direction of electrons, but that really hasn't caught on except in like AP calculus, or not AP calculus, like AP physics textbooks, but nobody really cares about them, at least the people that are actually using this stuff, so it hasn't really caught on. But for us, we are going to be using it in the traditional or the historical sense that it will be the flow of positive charge. Okay, will be the flow of positive charge. So those are some statements about current. And we discussed that as long as you apply a voltage, it will lead to the flow of charge. But this should lead us to ask the question, in a more quantitative sense, exactly how are they related? How are V and I related? Just because you know that applying a voltage leads to current doesn't mean you know that exactly how these two are related. The answer, the answer was provided by a guy named George Ohm, who saw that the current, so he applied different potentials and then measured the current. He saw that the current was proportional to the voltage applied, V. The only thing missing was a proportionality constant, and we know, or not know, but we call that now this R. V is equal to IR. This is one of the most important equations in electricity, so double star it, whatever you want to do. V is equal to IR. This is called Ohm's law. Ohm's law. Where V is defined as the potential difference technically it's supposed to be, it is delta V. But most people just drop this delta and just simply call it V is equal to IR. and everyone just recognizes that voltages are often a potential difference, not merely just the potential. Here, I is the current, and R is defined as the resistance. R is the resistance.
I just want to ask, that it says technically change V? right?
Yeah,
Okay.
technically delta
Delta V.
V. So R is the resistance, and this is essentially, the name itself is actually a pretty good description. It prevents flow. So the higher the resistance, the more the flow will be prevented. The lower the resistance, the less it will be prevented. Now let me help you visualize how to understand these three variables and how it's related. Who's ever drank a bottle of water? Hopefully everyone. Okay. But let's say, so you're drinking water, so it looks like this. And let's say the water's half empty or half full, whatever. If you're a pessimist or optimist or whatever. I don't want a hydro flask. Does anyone have a water bottle? Yeah, that one. All right. Okay, Isabel's got it.
It's half full.
Say you're, okay, say you're drinking that, right? But you're really, really thirsty. Okay, you're really, really thirsty. Instead of just flipping the bottle upside down, pouring it into your mouth, what can you do to make sure that the water comes out faster? You want to drink it much quicker. You can do what?
Squeeze it.
Okay, you could swirl it. Unfortunately, although that does work, it takes time to swirl, so you're going to be thirsty for longer before you get it. So no. Instead, what do? You
Apply
squeeze
pressure.
it. Squeezing. Why do you squeeze the bottle? Because you apply pressure, which makes it come out, right? So squeezing applies pressure so that more water is going to come out. This act of squeezing would be analogous to our V, the potential difference. So if we increase the potential difference, essentially we're squeezing the water. The flow of water is Ri. Is Ri. So if you squeeze higher, what's going to happen to your I? Or if you squeeze harder, what happens to the flow of water? More comes out. If you increase the potential difference, what's going to happen to the flow of charge? Increase. Right? These are analogous. But what about this resistance R? Well, in our water bottle scenario, there is actually something preventing the water from coming out, and that is the opening, or what I will call the orifice. This orifice restricts or limits how much water can actually flow through. This would be analogous to the resistance R. So, if you wanted to increase the flow of water, you can do two things. One is to increase V, or increase the opening, or lower R. So this is how to understand the relationship between these three parameters. V is like the squeezing of the water. I is really what we care about, and that's the flow of the water. And the resistance value, it's what prevents the water from actually being able to flow to its maximum capacity, and that would be the opening, or in the electronic case, the resistance value. Now, just like capacitors are an electronic device, there are electronic components which is simply existing to have a increase the resistance value and that is called a resistor. Resistor. And the electronic symbol, so it applies resistance to circuit. The electronic symbol for that looks like this. This is a resistor. And you guys will be using this on Thursday during the lab. But you might be thinking, if you've never used resistors or played around with circuits before, the whole point of resistors is to prevent flow. Now that should seem kind of contradictory, because the whole reason why you're making a circuit is what? You want charges to flow. So then why are you developing something where you want the charge to flow, but then you want a device that's stopping the charge from flowing? Do you guys see the issue? Okay. Ultimately, the answer is because, remember the LED lab where you guys were playing with it? Okay, when it was working, and like sometimes it kind of dimmed out and stuff, was the LED bright? Right, it hurt to look into it, right? That's because we had too much charge going into the LED. And it got kind of dim because some of them got blown out because you put too much current in. So technically what we were supposed to do was right beforehand, we were supposed to put a resistor to actually moderate how much charge was actually flowing through, so that it's not going to hurt our eyes or actually essentially destroy the device. Because batteries are standardized, like the 9-volt battery holds 9 volts, the power outlets here have roughly 170 volts. They're standardized to be very universal. However, not all appliances require the same amount of voltage. So, sometimes when you're working with a very small appliance, you don't need the full 120 volts to generate a lot of current. Or, if it actually does, you're actually going to destroy your device. That's where this resistors come into play. It helps you control the amount of flow. It's not to actually stop it, it's to control it. Does that make sense? It's to control the flow, not necessarily to stop. Alright. Okay, so this is called Ohm's law. That's very important. Now, one thing about Ohm's law is that despite its name, it is not a law. Ohm's law is not a law. Now, it was called a law because we thought it was, or not we, historically, that's kind of what it appeared. It seemed like this was just always universally true for all of the different materials that ever existed. However, we now know that it is not actually true. But it's true for a general class of materials. It's not a law, but how do I say it? But true for materials whose resistance is independent of V. So Ohm's law is only true for materials whose resistance is independent of V. Or alternately said, Ohm's law is true for a material whose satisfies Ohm's law, right? That's pretty much what it means. Luckily for us, most metals fall in this category. So most metals are considered ohmic. By ohmic, we mean R is independent of V. So we will be, for our purposes, we will be able to use Ohm's law universally without question in terms of calculations. I might, ask a conceptual question or two, but that's about it. How are we doing on time? Now let's talk about the units of resistance, because we will definitely be having to do calculations with them. Looking from this equation here, you can conclude that the resistance will have units of volts per amp. Volts per amp. Instead of saying volts per amp, in honor of this guy named George Ohm, we give it a Greek letter, capital omega, and this is called an ohm. So resistances have units of ohms. 1 ohm, 2 ohm, milliohms, omega ohms, so on and so forth. Let's do an example. Let's say you have this circuit, or this small section of a circuit. So we're looking across the resistor. I tell you the direction of the current I is that direction. And we'll label 2 points here, A and B. Now the question is, we want to compare the voltage between A and B as well as the current between A and B. Is the voltage of A greater than, less than, or equal to the voltage at B? What about the current? Is the current greater than, less than, or equal to the current at B? Let's first look at the voltages. Let's understand the current. It is the flow of what? So I is the flow of what? No.
Charge.
What charge?
Positive.
All right, positive charge. It's a flow of positive charge. Remember, it's the opposite of electrons. It's the direction, the opposite of electrons. If I is a flow of positive charge, and I is going from A to B, which one of these is more positive? Is A more positive or B more positive?
B. Because they're flowing to the right. Is it more positive?
Is so if B is positive, then you're gonna have positive flowing to the positive.
Oh.
Does that make sense?
Yeah.
No, it doesn't make sense. Well, yes.
Doesn't make sense.
Yes, it does not make sense. So A is higher than B. Therefore, VA is greater than VB. Because A has to be pushing the positives away, and only like charges repel. A has higher voltage than B. Yeah, so this is the answer. What about the second question? What about the current? Who says IA is greater than IB? Raise your hand. Okay, who says IA is less than IB? Raise your hand. Okay, who says they're equal? Raise your hand. and IA is indeed equal to IB because of conservation of mass. Well, let's connect the dot a little bit further. Conservation of mass, at least in terms of flow, tells us whatever comes in must do what? Whatever comes in must come out. Whatever is coming in here must come out there. Therefore, these currents are the same, and they actually have the same value as the current flowing through the resistor. And so, which we'll say also is equal to the current through the resistor.
What does a higher current change?
Huh?
What does a higher current change or a high current change when you're doing?
Well, high current doesn't change anything. High current is a result of higher voltage, but the more electrons that flow, the more more it can power an appliance. So, or it can make LEDs brighter. You guys have direct experience with that? It was really bright.
So what is the resistance at A and B different?
No. Well, okay, so in terms of the circuit, so when we draw a diagram that looks like this, we'll draw a capacitor and a resistor. Essentially, this is a very simplified sketch where the wire here, we're essentially saying the resistance is so small it's pretty much zero. So the resistance here and here is zero. Technically, it's not true. The next bullet point I'm about to write is, well, let's just write it. Okay. All devices and wires have resistance. So everything has resistance. There's nothing that doesn't except vacuum. But vacuum is nothing, so my statement is still true. Nothing has no resistance. So to answer your question, no, these at these points A and B, they would have the same resistance value. But what's stopping this this flow from being infinite is this here. So if you were to actually use this, use Ohm's law, you would have to compute I using Ohm's law across the resistor. And then this sets what the current at A is, as well as this sets what the current at B is. Does that make sense? So essentially, okay, let's come back here, okay? Do you guys know the thing where you have the two bottles upside down and then you do the tornado thing? You guys know what I'm talking about? Okay, instead of doing it for that purpose, let's say you immediately flip it upside down so the water accumulates at the top and there's no water down here, right? Yet. What determines how fast the water can go from here to here? It would be the opening, the size of this opening here. Whatever's flowing through here is also flowing through up here. Does that make sense? So it's the highest resistance value that determines exactly how much charge is flowing. In the same way, this is that bottleneck. Whatever is flowing through here determines what's flowing outside. What about how much flow is entering at this point? Well, it's whatever is entering here is what entered through up here. Does that make sense? So likewise, this also determines the current out here as well.
Let's see. Yeah, that does make sense. Thank
Question?
you.
So when you use a resistor, when we do it in our lab, it applies the whole circuit.
Yes.
Okay.
Yeah.
Even the stuff coming.
Well, okay. Well, it applies to the branch of the circuit. So you can work with circuits that look like this. So your circuits can be, pretty complex. If your resistor is here, this resistor will not impact this one or that one, but it will impact, this and this. Well, okay, it might actually impact these depending on what's over there, but just because something is here doesn't mean it will universally impact everything. You have to actually look at the circuit itself. Does that make sense?
What if it was
It
on
has the
the-
potential to.
Okay.
It has the potential to. Yeah.
What if it was on the outside?
Oh yeah, if it was here, yes, it will impact what happens everywhere.
Okay.
Yeah, so it has the potential to, doesn't always. Alright, where was that? Alright, so all devices and wires have resistance, not just resistors. And there is a phenomenon called resistive heating. Where as the electrons are flowing, because it's bumping into the atoms and it's, the bumping into the atoms is what what causes the resistance. But because it bumps into it, it causes heating, and this is how things like heaters and light bulbs work. This is how heaters and light bulbs operate. But this should lead us to ask the question, what determines the resistance of an object? Or what controls the resistance of an object? So not everything has the same resistance value, so we need to understand exactly what are the parameters in determining what resistance value an object has. The answer we're going to come from or explore is from experiments, meaning people ran experiments and this was just the empirical fit that came out, as opposed to theory fundamentally established. So it turns out the resistance was a function or depended on the material itself. So different materials have different resistances. But coming back to this metaphor here, if we increase the opening, the water would be able to flow faster from the top to the bottom. Likewise, the cross-sectional area can also change the resistance. Also, it will be the length as well. So when you put all this together, you're going to get an equation that looks like this. The resistance is equal to, this is the Greek letter rho, not P, okay, Greek letter rho, times L over A, where rho is defined as the resistivity, and this is the material dependent one. A is the cross-sectional area. And L is the length of the material. Now, silver is the most conductive, meaning it has the least resistivity. Silver is the most conductive, meaning it has the least resistivity. Let me ask you guys a question. Wires, would you want to have high resistivity or low resistivity? Wires. High or low?
Depends.
No.
Huh? Well, generally speaking, what is it typically used for? Yeah, it's just to make sure that all the different components have the charges going where it needs to. So, is that carried out through high resistivity or low resistivity?
No.
Low. You want low. Who knows what wires are made of? The most common wire material.
Copper.
Copper. But silver is the least resistant. Why do we use copper? Why aren't we using silver?
Silver would break.
No.
For more controlled flow.
No.
Expensive.
Yeah! Silver, but expensive. Now this is very important because as you guys are going to be going into the workforce, you have to keep this distinction in mind. Your job is not about being the most efficient. What it is about is being the most cost efficient. Do you guys get the difference? Businesses only care about money. Okay? You just want to be the most cost efficient. The advantage you get of using silver does not outweigh how expensive silver actually is. Copper is a quote-unquote close second. By the way, it's actually not that close. Silver is like up here. There's a bunch of things down here. Copper is down here. Silver is way up here. So copper is a close second, but cheap. That's why it's commonly used. Therefore, common wire. However, there is another material that is commonly used as a wire, and that is aluminum. But aluminum has quote unquote high resistivity. Why do you think aluminum might be used?
Super cheap.
No. I think it's comparable to copper, but that's... Oh, by the way, it has high resistivity, so it leads to fires more often. It leads to a lot of other issues. But still, people use it. Why do you think that might be the case?
Whatever's being made needs a low amount of volts,
No.
so like low energy.
No. You still want a wire so that essentially you don't want the wire to take away you don't want the wire to have the resistance. You would much rather just put a resistor to do that. So you still want a wire for its low resistivity. However, there is still aluminum wire, even though it has high resistivity. So what's good about it? Any ideas?
Does it have something to do with magnetism?
No. Apparently nothing's good with it.
Would it like heat stuff up better?
Well, yeah, but you don't want to do that because that means a fire in the house, which is bad, right? You actually don't want it to heat. That's
Come on, guys, we can get it.
what is true about aluminum.
Something about heat resistance? I don't know.
No.
One thing's out there.
Recycle it.
No, I think you could recycle copper also. But it is lightweight. So there's going to be applications where you actually care about the weight. And so that's where aluminum comes in. So specific appliances do actually use silver, believe it or not, for wiring. And you might think that's like so expensive. Yes, but this is for things like pacemakers where you really, really need least resistivity. And would you not pay, if it keeps you alive, to use silver wires? And the answer is of course. So for very technical and very precise things, silver must be used because of its resistance, even though it's expensive. Where did I get to? Oh, that's where I get to. All right. Let's do an example. Man, I wish there was chalkboard still. Because I would use the chalkboard if we had a chalkboard. I don't like whiteboards.
Why?
And chalkboards, you can actually have different techniques using chalk. I don't know if you guys have ever seen it. But if you like angle it correctly, you can actually get nice dotted lines to show. And obviously for science, you know, making different lines on graphs and sketches is very important. Yeah, whiteboards don't allow you to do that. Yeah. So, if you guys want to help me out, start a petition to get blackboards back into the class with chalk. Very much appreciated. Alright. So, yeah, interesting factoid. There are like mathematicians who are hoarding as much chalk as possible because they foresee like whiteboards taking over. So they're just like storing good chalk. Yeah. Okay, this is just an example from the textbook. Who knows what a stereo is? You guys all know what a stereo is? Alright, it's something that just plays music. Okay. Or just connects to the radio. Right? You want to connect, let's say your stereo. Who has a stereo? Does anybody? Wow, really? Wow. You want to connect your stereo. Does it still work?
Yeah.
No, just
We still use it.
Oh, really?
Yeah, we have a lot of old stuff.
Oh, okay, interesting. You want to connect your stereo to speakers. Say A, if each wire must be 20 meters long, what diameter of copper wire must be used to keep resistance below 0.1 ohms. B, if the current to the speaker is 4.0 amps, then what is delta V? So you want to connect your stereo to speakers, and you have a length requirement of 20 meters in terms of the wiring, as well as a resistance requirement. And so we want to know what is the thickness or the diameter of the copper wire that we can use based on those specifications. So here, we want to know the diameter is equal to what? But the information that we're provided, we have a resistance value as well as a length. As well as we're specified copper. Here, let me give you the resistivity of copper. So rho copper is 1.68 times 10 to the negative 8th ohm meter. And we're specified copper, and that should immediately tell you, you know what your resistivity is. And from here, you should be able to ascertain that the expression that you're looking for is our resistance equation. And so R is equal to rho L over A. And further looking, we know that the A, the cross-sectional area, is going to be pi times d over 2 squared. Right, pi r squared. And radius is diameter divided by 2, or simply pi d squared over 4. So if we were to put this in for our A, then we would get R is equal to rho L times 4 over pi d squared. And when we isolate for our diameter then, we get diameter that is equal to square root of 4 rho L over pi r. And as long as you put in the values correctly, you should get a value of 2.08 millimeters. So that is the diameter that will lead you to meet the specifications. Then the second question is asking, if we want the speaker to be 4 amps, or if the speaker has 4 amps, then what is the change in voltage throughout that entire speaker? And for B, we want delta V, and we're given the current as well as we know the resistance R right here. And so this looks like a Ohm's law problem. V is equal to IR. So this is going to be 4 amps times 0.4 ohms, 0.1 ohms. 0.1 ohms is a resistance, so we get a value of 0.4 volts, and that will be the final answer. And the last thing that we'll cover is what is called electric power. And this is section 2D, I believe. Yeah, section 2D. So when we turn on an appliance, we are said to be powering the appliance, not energizing the appliance. Now, energy is more fundamental, and energy and power are related. But what is power? They are not the same thing. So energy is related to power. And it is in this fashion. Power is simply the amount of energy that you are providing per time. Energy per time. So when we're for an appliance to work, you actually have to give it enough energy in time, like per time, for it to actually turn on. So that's what power actually is. You are giving it energy, but when we say something requires a lot of power, it means it needs a lot of energy very quickly, or else it's not going to turn on. Okay. For electricity, this is the second important equation, just like Ohm's law. In electricity, P is equal to current times the voltage V. Oh, I forgot to mention. So the units, energy per time, so it's joules per second. Well, we call this a capital W for a watt. So you might hear watts, like 1 watt, 2 watts. So electric power is I times V, current times the voltage difference. Of course, we can use V is equal to IR, we can use Ohm's law, and transform this into P is equal to substitute IR in for V here. And you're going to get P is equal to I squared R. Or alternatively, instead of V is equal to IR, we can replace I, just rearrange Ohm's law a little bit for V over R, and you'll get P is equal to V squared over R, and those are alternate forms. But the one that I would just remember is P is equal to IV, so double star this one, because that's technically the definition. The other two, you just know Ohm's law, and then you can transform it into one or the other. And this is all the calc-based class got to. No, we didn't do anything else after this. Of course, on Wednesday, after going over the quiz solutions, we'll begin to cover this a little bit. All right, I'll see you guys Wednesday.
Quick up.
Yeah.
What's the sensitivity concept?
Where's this picture?
I was reviewing like digestive material from my previous lecture.
You mean epsilon naught?
Yeah.
It's, so electric field, when it moves through space, okay. So the electric field is it's a distortion of space, right?
Yeah.
So if a material, let's say something was here,